All right, so it's going to be a little bit more math this time around, but it's not going to be that bad. So we're going to be, the most complex thing we're going to be doing is derivatives. And derivatives is basically the rate of change of a function at a particular point. In particular, we're going to be looking at gradients. And then a little bit later, backpropagation. And backpropagation is a way to solve for the gradient that computers find really easy. And what a gradient does is that it describes the direction of the fastest change. Fastest change direction. So what it's actually defined as is usually done by this symbol here, which is an inverted triangle. Let's say phi is a space that has variables x, y, and z. It's the partial of the field in terms of x in direction I plus partial phi, partial y, j plus partial phi, partial z, k. Now, if you're not actually sure what I and j, if you're not used to this sort of notation, don't really worry about it. All it means is just like 3 different dimensions. So what does that mean? So imagine 3 dimensions. 3 dimensions, x, y, and z. What this could be describing a system of temperature in a room. So in a room you have hot temperatures over here, and then cold temperatures everywhere else. And the gradient would describe the direction of the biggest change from hot to cold or cold to hot, something like that. Now, if we're instead thinking about 2 dimensions, a classical example, let's just say x and y, could be, I'm just going to write here, temperature, could be topography. Right? So you have x and y, so like map view, or you could even, in this case, call it longitude and latitude. And for each direction, you have a particular topography, for example, if you're familiar with topography displayed in this way. So you actually have a direction here, which describes the greatest change. Among this, we also have something called a directional derivative. Now, what that is, it describes the rate of change along a particular direction. And that is described as, let's say, the derivative of phi across the length s is the gradient of phi with the dot product of a particular unit vector u. And a unit vector, for those of you that need a bit of a refresher, is just simply a vector that has a length of 1. And what you can do is, if you don't remember how to calculate a unit vector, let's say you have a vector a, it's a divided by the modulus of a. You can also have a directional derivative that's based on an angle theta. So instead, you can have something that looks like this, which is the modulus of the gradient, phi cosine theta. So you start off with a gradient in this direction, so gradient phi, and you're particularly interested in what the directional derivative is in a particular direction unit vector u, and it's separated by a certain angle theta. You can actually use this property right here. Now, what does it actually mean? So if we think about our definition of what a gradient is again, so a gradient phi, say x, phi x I plus phi yj plus partial phi partial z k. What this means is that it describes how much of an impact this particular variable have on this rate of change, right? So our rate of change, so let's say we have a particular value here for x and we change it a particular amount. We know by that amount how much the rate of change will vary. So how does this apply to deep learning? We're going to look at this a little bit more in just a second. What this means is that for each of our variables, we can see how we are transferring along our stochastic gradient descent. So we'll know how much of these, how much weight each of these parameters will have. Any questions so far? Okay, just stop me if you have any questions. That's totally fine. I don't take it personally. So gradients can be calculated in two ways. They can be calculated numerically or analytically. So numerically, it's actually pretty easy. So let's say you have our function phi. Let's just say it just varies on x, doesn't really matter at this point. dx, it's not a partial anymore, it's just a derivative. We can use the limit, let's call it variable h goes to 0, so h is very, very small. Phi of x plus this h minus phi of x over h, right? So we're trying to see, we are comparing the difference in phi by whatever this small step h is, right? Where h is very small. Now, the pros of this is that it's simple to do, and you can, it's a numerical answer, like an easy numerical answer. Now the cons is that one, it's an approximation, and this is computationally expensive. So in deep learning, we don't actually solve this using numerically. We don't solve the gradient numerically. We solve it analytically. And the process by this is called backpropagation. Now, backpropagation is very easy for computers, but kind of tricky for humans to wrap their heads around. What it does is that we're solving for gradients by essentially the chain rule. So hopefully you guys remember what the chain rules of derivatives are, but in case you don't, we're just going to be going through it right now. And we're going to be going through it using an example. And I'm actually going to clear this up a little bit just to make it a little, give myself a little bit more room to work with. And what we're going to do is we're going to start with a simple function that varies on 3 parameters. So this could be our temperature. We're going to have x, y, and z. And very simply, this function is going to be x plus y multiplied by z. And we have x is equal to -2, y is equal to 5, and z is equal to -4. Okay? So to actually better understand this, because again, it's difficult for humans to think about this, I'm going to do what is called a logic gate. So I'm going to draw things out in a way that should hopefully make a little bit more sense. So I'm going to put our variables x, y, and z over here. And we know it's x plus y, right? So we're going to have an addition operator over here. And x and y are going to feed into this and be added. And then we're going to have a multiplication operator over here. And the result of the addition is going to feed into this multiplication. And then the output's going to be here. And what I'm going to do is, the way that to do this is you first solve, you basically propagate these initial values across the entire logic gate, and then you work your way backwards. So the first thing is something called the forward pass. What I'm going to do is I'm going to write the forward pass up here on top of the arrows, and the back propagated component is going to be here at the bottom. So we know our x value from our problem is, I'm actually going to write it in blue, is -2. So I'm going to write it over here, -2. We know that y is equal to 5 here, and z is equal to -4. So the first thing we can do is we can see at this logic gate what the operation is. -2 plus 5 is 3. And then we have this multiplication here. So -4 times 3 gives us 12. So our forward pass is done. The next we do is that we label our operators. And what that means is that we're going to come up with new ways to describe these particular functions. Because what we're going to be doing is we're going to be doing the chain rule to solve what the derivative is. So we're going to call this Q, and we're going to call this F. And then the last thing we're going to do is that we are going to identify the partials and solve. Now this probably seems a little bit confusing, but we're going to go through it. And what we're going to do is at each step we're going to label what's going on here and all of the partials that we have, because we don't have just partial x in terms of f and partial y in terms of f. We also now have a partial of q. So what we have is 1, 2, 3, 4, and 5 partials to solve. So the first partial is partial f with partial f. The second is partial q with partial f. Oh, no, it's partial f with partial q. The third is partial f with partial x. The fourth is partial f with partial y. And the fifth is partial f with partial z. And so it looks kind of scary right now, but I promise it's really not that big of a deal. We're just doing very, very basic operations. So let's take a look at this, right? So the first part is the partial of the function with itself. So it's sort of like saying, you know, dx, it's like the derivative of x in terms of x. So df partial of itself is equal to 1. And so what we're going to do is that we're going to write what is called the backpropagated component here at the bottom, so we keep track of it. Then we have this partial f with partial q. And we already said, okay, well, this is kind of equal to, we said that q is equal to this, right? X plus y. So really, what this is kind of equal to is just z, right? Because we have q times z in terms of q, so we just have z left. And z we know is -4. So df dq is -4. Okay, now let's look at what happens in x. Well, partial f over partial x is actually just equal using the chain rule. And this is where sort of when we're actually applying the chain rule is equal to partial f partial q times partial q partial x. And so we've already solved what partial f partial q is. It already knows it. We said it's -4. So it's -4. And if we look at here, q is equal to x plus y. So if we're taking this derivative in terms of x, y goes to 0. So we just have 1. So this here is equal to -4. So here we've already figured out what the partial x for our function is. Let's do the same thing for partial y. Using the chain rule, we know that this is equal to partial f over partial q times partial q over partial y. Again, using the same thing that we got over here in equation 2, we get -4, and that's x plus y. This time, it's in terms of y, so x goes to 0, simply 1. And our result is -4. So that's it. And lastly, we have partial f in terms of partial z. Okay? And what this is you have to think about this now in terms of q again. And you say, okay, well, it's q times z taken in terms of z. So that is just simply q. Or x plus y, or -2 plus 5, which is equal to 3. And that's it. We've backpropagated and solved the analytical gradient for this function. Now, what does this mean in practice? Let's take this guy right here. Let's take here partial f over partial x is equal to -4. What this means is that if we increase x by a little bit, then our entire function is decreased by 4 times what that little value was. So if we have a small value a, if we do something like x plus a, then f of x, y, and z is decreased by 4 times that value